First, I would thank the organizer, especially Dr. Amin, for inviting me to give this talk. And this is the first keynote talk in my life, as a virtual conference. And it's also very special here at the United States. It's a Thanksgiving Day, so it's a really good memory to give a talk in this situation. Thanks again. And so today I will focus on the very special topic that of the interfacial material development for the energy storage. So some of the big picture, as you see that energy storage play very important role. And 10 years ago, we may have some idea it will play the important role. Right now, more and more people are convinced that energy storage play very important role, no matter in the transportation application or the grid energy storage. So the overall energy storage is a very big topic. There are a variety of the chemistry, technology, and so for the energy storage, depends on the application, either can be used for energy management or power control, okay? So for the large scale application, energy management is where the high energy density, the longer discharge, the time is needed, like the flow battery, the sodium sulfur battery, but rechargeable battery, which including a few types of the battery, can be used either for energy management or power control. So that is one of the key area, the industry put efforts. For example, the lithium ion battery, the lead acid battery, and so the Carl mentioned this potential zinc battery, zinc manganese battery. All these battery can be used for either energy storage, grids, or transportation. So lithium ion, actually, we know that lithium ion has been used for almost the 30 years commercially. So we have a lot of the application. I will not focus on this one, but when we talk about material for lithium ion, so we know that it composes a cathode with a high potential and an anode. So when you combine these two materials, you get the cell, and with the electrolyte field, you can cycle it reversibly with pretty high efficiency for the energy efficiency for lithium ion. But when we look at the next generation, the chemistry that potentially can either reduce the cost or increase the voltage, increase the capacity from cathode side. For the anode side, there are more options. So you have graphite, you can go to different conversion based this electrode if you do not care about the efficiency, but of course you can go for very high capacity, silicon and lithium. So this is give the very different very wide portfolio that you can combine them into different in the cell. So in my group, I focus on this new material, especially for the lithium ion. We work on the carbon silicon and also cobalt, especially recently on low cobalt, no cobalt. And for the lithium metal, this is an alternative, the anode, that potentially can replace the graphite and bring this energy density to another level, for example, above 300 or reach the 500 watt-hour per kilogram at the cell level. So this metal, and when you pair the lithium metal, you can choose different cathode. Okay, stationary wise, we also have some project working on the battery for station application. But today I focus only lithium metal. So because the topic is about the interfacial material, so I will present some of the work focus how to manipulate this interface for lithium metal by different approaches. Especially, I focus this cell, the lithium metal paired with the cathode. Okay. So this is the outline of my talk. There are two parts. First one is how can we develop some of the polymer we call the reactive polymer composite to protect the lithium against this reaction with the electrolyte during the cycling. So basically, this is an interfacial material that can make a new type of SEF for lithium metal. And the second part is the one we recently developed, we call the electrochemically active monolayer. So this is a monolayer and can also be used to manipulate this ICS. It's a very interesting result. So first part, so go on to the lithium metal. We know that the metal anode, no matter lithium metal and the zinc, and so they more potentially have the dendrite. So basically, it's in homogeneous nucleation and the promotion of this inhomogeneous the nucleation and the growth from this the dendritic the morphology. So the one of the key the reason for this one is the ICI. So the ICI is not stable, and when you have this high current density promote this the nucleation inhomogeneous, this ICI can be broken, promote this uniform the growth of this nucleation, and then promote the dendrite form. So then the ICI is very important, but typically the ICI formed on the anode side, especially graphite, is very dense, uniform, and very thin. But for anode of the like lithium, it's not that case. Okay, so then that's why we want to see, can we use some of the proactive approach to stabilize this anode, especially for lithium? So can we put some function group? Can be polymer, can be any the oligomer functional material on top of this anode, and then through this electrochemical process, so then this material can participate from a more different, okay, or stable ICI. So that's a key idea. So we have tried a few approaches. So for example, we developed this sulfur-containing polymer. So basically that is chemically reactive against the lithium metal from this organic sulfide and lithium sulfide. So this can be used as a ICI component, especially for lithium sulfur battery. And we try this, bring this, cyclic ether, this the solvent. This is a solvent in lithium used for this lithium battery. Can we bring this functional group of cyclic ether into this the polymer, so then it can use to manipulate this ICI. So this is, can we incorporate some of this ion conducting material, for example, this lithium cell phosphate. So when we have this polymer, when it decomposed, so then this sulfur bond break, you can have this lithium, this the cell lithium the cell phosphide. Okay, so this is some of the work we have done before, but today I focus one topic that especially addresses more engineering issue is lean electrolyte, because typically if the ICI is not stable, so then during the growth of lithium metal, during the deposition and stripping, so then the ICI is broken, so then you expose new surface. This new surface of lithium will react with the electrolyte. So that's a key issue, is that if we have a cell with a flooded electrolyte, you can make the cycle over 100 cycles. But in reality, we cannot add too much electrolyte. Otherwise, the energy density of this lithium cell will be decreased. So we have to control the amount of electrolyte. We call it lean electrolyte. Okay. So typically, lithium ion battery, the lean electrolyte condition is less than 3, okay, or 2 microliter per milliampere hour. So we have to decrease this. But if you use a lean electrolyte, you can see this, because the cell continue to consume electrolyte. So when the electrolyte dried out, cells start to die. Okay. Also, you found this dendritic lithium. So it looks like it's a black layer on top of lithium metal. So that's the key issue when really try to apply this lithium metal practically in the cell. So what we developed a couple of years ago is that we try to develop this the polymer that can contribute to ICI formation, and at the same time minimize the electrolyte contribution in the ICI formation. So that's a key idea. So what we use this polymer is that when we have this polymer, so here is a 2 function group. One is a softening fluoride. So this softening fluoride, chemically, it can react with the lithium metal, generate lithium fluoride. We don't need this electrolyte, a lot to participate on ICI formation for generating lithium fluoride. So the polymer itself can. Okay. Also, we copolymerize with a cyclic ether. This is a DOL. This is a common solvent for lithium metal. So when we incorporate this block, so we have a co-block polymer. Both these block can chemically react with lithium metal. Okay. Of course, can electrochemically react with the lithium metal. So form ICI. So then the good thing is that we, intrinsically generate lithium fluoride passivating layer. Okay. And then when we have a polymer and coated, so at the beginning, we can promote this homogeneous formation of ICI before you cycle the cell, okay? And then we can add some other additives. For example, if you think about the mechanical property of this SEI layer, we can add this mechanical filler, for example, graphene oxide, to enhance this mechanical property of this reactive polymer composite. So that's a kind of the strategy we have for developing this polymer. So let's look at the result. So this is the top view, of this polymer coated lithium metal. You can see the cross section. You have this thickness of this composite layer around the 2 micrometer thick. So then you can see some layer structure because of graphene oxide. So this is a morphology of the lithium metal in conventional electrolyte. You can see it is a mossy-like structure. But then when you especially look at this interface layer, okay, this interface layer, we can strip of this lithium and then flip this sample, look at the interface. You can see here, this is a SEI layer of this polymeric SEI. So you can see there's a lithium fluoride. Okay, so there's a strong portion of the lithium fluoride. But in conventional electrolyte, you can see the lithium fluoride amount is much weaker than lithium carbonate or lithium, this type of the lithium. So this is give the difference on this SEI formation. Of course, because we have polymer, when you look at overall elemental distribution, so typically the electrolyte drive the SEI, we do have a lot of the inorganic portion, lithium fluoride, lithium oxide. But then for polymer SEI, not only we have lithium fluoride, but we have a polymer. So then you have more carbon in this SEI. So this is a change the composition shift from the more inorganic to organic, but still with the lithium fluoride, which is one of the best components for stabilizing the lithium metal. So then when you look at the depth profile, okay, so here, this is the coating. When you look at the depth profile, basically is you sputter the argon ion, and then look at this the sample from top to the bottom. So then at the top layer, so when we look at the fluorine and the lithium, okay, signal, so then you can see the softening fluoride. This is the softening fluoride peak. Okay, so this is the top level. And then when you go down to the interfacial layer, so this is the interfacial material generated by reacting with between the lithium and the polymer, you start to see the lithium fluoride. Okay, and then also from lithium side, you start to see the lithium fluoride and the lithium oxygen, the binding energy here, and then all the way down to the bottom, of course, you get the lithium. So there's nothing signal here. So you can see the polymer itself, when the interface formed, so they have this, the interfacial layer. But then there's also on top of this interfacial layer, unreactive polymer served as a reservoir, can continually contribute to the SEI formation during the charge discharge, especially when the volume change of lithium is huge. Okay, so then we can look at the cryo-TM. So here this is a cryo-TM. You can observe this the lithium metal, and especially the lithium metal, the lattice fringes. So this is the interfacial layer. This is a polymer, and this is a lithium metal. Within this, this dashed line of this box, brown box. So here we can see the lithium fluoride nanocrystal. So especially lattice fringes of this lithium fluoride. And then, of course, you can use EOS and STEM. So then you can differentiate the lithium layer and the interfacial layer and the polymer layer. So here, this is a lithium KH EOS spectrum. This is a signature of this lithium fluoride. And as I mentioned, one of the goal for this development is that can we make this lithium metal cell cycle at a linear electrode? Can we make it a cycle more stable? So when we look at the morphology of this lithium metal from the top view, so there is a layer of polymer coating. So it's 200, 300, 400, and 500 cycles. So polymer layer is still there. So after long cycle, so you can see some of the wrinkles, but the polymer overall morphology is stay on the lithium metal. And then you can see its cycle more stable, than the biolithium metal, especially at the linear electrode condition. And especially when you control, by this photograph, you can see this polymer coated on lithium metal after cycle. This is a 50 cycles. You still can see the very uniform deposition of lithium metal. Okay, without observing this mossy lithium. So that's an idea that interfacial material can be developed by some of the reactive polymer composite. The second part of my talk here is we developed some new technique for formation of the ICI. So we call the electrochemically active monolayer. So here, when we look at the lithium deposition on the current collector, so here, especially, at low temperature, it's, very easy to promote the dendritic growth of this lithium metal, because ion transport is limited during the low temperature, kinetics poor, and the kinetic for the interfacial layer formation is also very slow. So, then it's very easy to form the dendrite. Okay, but then if we modify this current collector with a monolayer, okay, with a monolayer, and then if we design this monolayer with some of the electrochemical label group, okay, so then this label group can generate some of the component that can beneficial for formation of the good ICI. So that's the idea. So the key is how to design this molecule. So we identify this benzene bisulfonyl fluoride. So we still use this sulfonyl fluoride, the chemistry. So then it can, when the lithium deposit, so that it can decompose, okay, generate lithium fluoride, and also provide some of the lithium philic molecule with the lithium ion here. So then promote this nucleation more uniformly of this lithium metal. So then later you can see the ICI will be different, okay, between these the scenario. So let's look at some of the result. When we look at the deposition of lithium metal on copper, okay, so here is a -15 deposition, low temperature deposition. You see the beautiful dendrite, okay. So this is naturally formed this the needle shape of the nanomaterial, the sub-nano material. And then, but when you deposit the lithium metal on this modified copper with this electrochemically active monolayer, you can see they perfectly form this island, spherical, the lithium metal particle. Okay, this is the nucleation of this lithium metal is completely different. Okay, so but if we look at the three-dimensional matrix, so this is a copper host. Okay, with this without this modification, this copper mesh, and here you can see after deposition, so you can see the morphology is different. This is a more uniformly filled pore by this lithium with this modified the surface. Well, in contrast, so then you see some of the aggregation of the particle of the lithium metal. And then the key is why this molecule can work. Okay, so here we use this cell function group, so then we can easily form this self-assemble monolayer. Means that they have highly packed the arrangement of this molecule on the surface of this copper with the monolayer formation. But here we try to answer why this molecule work. So we design a different type of this monolayer on top of the copper. So here you can see this is an analog of this similar structure, but with this lithium ion. So this is hydrophobic. So we also generate this is this one with a fluorine, okay, with a fluorine function group. So this is a control. And then, but when we look at the nucleation, so we still observe that even though with this one, especially this one, you see some aggregation of this lithium in try to form this aggregate the island, but still we observe the dendritic this nucleation. But especially for these molecules, we can observe this few particle of lithium metal. So that means the monolayer can help, but especially this electrochemically labeled function group generate lithium fluoride is very useful to generate this uniform island type of sphere particle of the lithium metal. So then we can look at the interface. Okay, we can look at the interface of the lithium metal by cryo-TEM. So here this is a lithium metal, and this is a ICI. Okay, so this is a conventional ICI of this lithium deposition on copper. You can see very big crystal, within the interface, 2 to 3 nanometer of lithium oxide, lithium carbonate. Okay, we randomly observe some lithium fluoride. But with this monolayer to manipulate this interface, and we can observe this multi-layer structure. So this is a lithium fluoride rich interface, okay? And then there's a middle layer, outer layer. So our layer is more amorphous. In the middle layer, we observe some of the nanocrystal of the lithium fluoride, lithium carbonate. So you can see some of the lattice fringes, okay? So here the key is that with the conventional the deposition lithium on copper, you form highly crystalline domain of the nanoparticle inorganic. But this one we form this multi-layer, okay? So then it's more clearly you can see some more in-depth calculation. So this is this dark field, okay? This is a stem, okay? This is a dark field of this interface, and then we select a different area. We select a tiny area to do the yields. So you can see this area is a lithium metal. So this is a peak significant picture for the lithium metal. This is the inner layer of the interface. You see the signature of the lithium fluoride. So this is a middle layer, and this is the outer layer. Okay, so then you can see spectrum is different. Especially here, this is signature that inner layer is a lithium fluoride. Again, we can use EDAX. We can see some of the sulfur, copper. So all these monolayer compounds stay on the copper and on this interface. Okay, so actually you really can observe lithium fluoride. So it's really hard to get this image. You have to pick up this condition well because you want to get high resolution at a cryo condition is a little bit of a challenge. But we do manage to get some nanocrystal lithium fluoride, lithium carbonate. This is the middle layer. So here to prepare the sample, we coat the carbon layer on top. Okay, this is a carbon layer. So this is a SEM middle layer, outer layer. So this is their interfacial lithium fluoride rich lithium interface. Okay, so overall, so through this in-depth calculation, we want to confirm we do form this multi-layer of this interface by using this EAM, electrochemically active monolayer. Okay, so then again, if we change to this inactive monolayer, okay, not this the active monolayer, inactive monolayer. So we can see again, we cannot observe this lithium fluoride rich multi-layer, this SES. So we still observe this aggregation of the nanoparticle MASEC type of SES structure in the lithium oxide fluoride carbonate. Okay, so that is the advantage that interface formation can be controlled by this interfacial material. So typically electrolyte decompose from SES. So there's a kinetic of the decomposition process, transport process crosses interface layer. But this is the advantage that the interfaces can be controlled by pre-anchored interfacial material. Okay. So then when you look at this cycling, so after cycle of the lithium metal on copper, you strip off all the lithium, you can see the deposition of this dead lithium or waste SEI. So that's why, when you use this copper after cycle, you see a lot of SEI, this waste. Okay, but then with this EM modified copper, the surface is much clean. Okay, the first is much clean. So this is 200 cycle, 50 cycle. So there's still some aggregation, but the surface is much clean compared with the bare copper. And again, so this is at a little bit of micron scale, not nano scale, look at the SEI. So I want to focus still on the fluoride. So here, this is SEI on copper, SEI on copper at minus 15 degrees C. Okay, so this is room temperature, this is minus 15. So this is SEI on this EM copper with minus 15 condition. Again, we want to focus on lithium fluoride. Okay, so there's a significant amount portion of lithium fluoride against the other type of the fluoride species. Okay, so this is again tell us no matter low temperature and even at high temperature, I did not show it. So it helps form a more stable structured interface to stable this lithium metal. Another advantage for this EM copper is to prevent the copper corrosion. Okay. So copper corrosion, because as you form non-uniform nucleation of lithium metal, so you naturally form some short circuit between copper, lithium metal, and electrolyte. So there's a corrosion. If you have bare copper, put the lithium metal, charge discharge, you can see there's a kind of current, okay? The very tiny current, and they promote the copper corrosion. But with the EM, so this current is pretty low, okay? And the more obvious is that we want to look at this self-discharge. So this basically is that when you have an anode-free cell, okay, copper with the cathode, copper, EM copper with cathode, so you charge, okay? And then you charge it to 4.3, for example, and you rest, okay? So basically this anode-free cell, when you rest, there's a corrosion, that unstable ICI, so this voltage will drop. Okay, maybe just after 20 hours. Okay, you can see voltage drop, to below 4 volts, and after longer time voltage continue drop, that you cannot use the cell further discharge it because voltage is too low. But with this EM, we can keep this voltage above 4.1 volts for 300 hours. So actually we have another static example, more than 2000 hours. Okay, so that make it this corrosion is the prohibited, so they make this the self-discharge minimized. So after 300 hours, you still can discharge the cell. Okay, so that's the advantage of this EM technique. Again, with this technique, we can cycle this lithium metal cell, at low temperature and also room temperature stable. So here, this is a minus 15 degrees C cycle, and then switch to room temperature, minus 15 cycle switch to room temperature. So both room temperature and low temperature, you can cycle it stable with this protected lithium metal. So this is a little bit different from graphite. For graphite, without the very special ICI electro additive, it's difficult to cycle across this low temperature range to the room temperature range. So again, I would say that the different technology have a different need, but for lithium metal and other type of anode, this interfacial is manipulation or interface engineering is very important. So we can start from the other angle, see if we can actively put some interfacial material under this anode to protect this, make it stable. And so that's my talk. And again, thank you. And this work was mainly supported by the DOE project. Okay, thank you.